Cool.
Yeah, you're recording. Excellent. So we'll go through this. I don't know how I put these together last night. I know we've only got 20 minutes. That might be a little bit fast. So we'll go through these fast. And if the end result of this is that we need to go back over something or not, and a little bit of a review of what we talked about last time. But I figured it was just putting it all in one presentation would make sense for anybody else that wanted to attend or watch. So basically, the goal here is to kind of keep it simple and go over the basics of glTF. I think I've got a list here of what I'm expecting to get out of this. Core concepts around polygonal 3D models, and this is very specific to a particular type of 3D model and not other types of 3D models, which kind of can make this a lot more complicated. The storage options for glTF. There are a few. The ability to actually look at a JSON glTF file and understand what it is, what's in it and what it's trying to say, and maybe some insight into how data is packed within the binary portion of a glTF file. So those are hopefully the takeaways. And again, as we go through this at any point, if you want me to stop, if you want to ask a question, please feel free to do so.
Okay, sounds good.
I'm kind of going into my my presentation mode, so mentally. Starting off in this first section, talk a little bit about geometry. Again, we covered some of this last time, but as a quick review, 3D data, polygonal data really starts with this idea of individual vertex points, XYZ coordinates, and a list of these would be our vertices, and our vertices are sort of the base foundation for polygonal 3D models, and that is specifically models that use polygons, multi-sided surfaces as the data to represent the 3D data. There are other types, just the same way that there is pixel graphics and there are vector graphics in 2D. There are ways of representing shapes by points in space with really interesting curves or equations to represent. You can imagine an equation for a sphere, and y squared plus x squared equals 1, and using that as the representation of space. And so then you can zoom in as far as you want to get as much detail as you'd want. You'd still have a perfect sphere, which is the vector-based version, whereas this is very much based on a unit system, usually, and for glTFs, 1 meter is 1 unit. So in this example, this cube would be a 1 meter by 1 meter by 1 meter cube, and if you zoomed out or zoomed in, it remains at that unit size, and the scale or the precision is not going to change beyond what the original vertices are. So in order to store these vertices, I've got the vertices listed there as on a square. They would represent something like these parentheses values of 0, 0, 0 to 1, 1, 0, representing these 4 vertexes, individual vertexes. And then the list, if we were to store them, we might store them in an array, where they're just written out 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 0, being the representation of those. And we would know, because we said that they were vertices, that every third is the start of a new vertex, a new X position. Usually these are stored as floats. You could do something differently, but generally for what we're doing, these are floating point values. And then, so if we wanted to define a surface, something like a square here, we can define the surface as 2 triangles. In this case, we have 3 vertices to represent each triangle. So V0, V1, V2, each one of those is 3 values, so an X, Y, Z. So for this first triangle, we've really got 9 values, and then so we've got another 9 values here. So in this example, we have 18 values used to represent this particular shape. It's important to note that order as you define these vertices on a triangle is important. So we want to be able to know in 3D space whether or not this is the front or the back side of a surface. And so clockwise, so in this case, 0, 1, 2 represents a clockwise rotation and would be in this structure facing towards you. And then in this one where it's 1, 2, 3, going counterclockwise, this would be facing away from you. So if you actually built this directly with 0, 1, 2, 3, and you define this as V1, V2, V3, you're defining this in a way that the end result is going to be facing away from you. So what you'd actually see in something where back face was cold, you would only see a triangle, and then flip it over to the other side and you'd see the other triangle. So if you wanted to actually make these both facing towards you, you would need to have the order on this here be, instead of V1, V2, V3, you would say it's V1, V3, V2. Obviously, you could also do V2, V1, V3, but this is just the representation of 3 points, three vertexes to determine what a triangle is. There are other ways to define surfaces. A common next step would be this idea of triangle strips or triangle fans. The advantage of those is, instead of in this previous case where we had to have 6 different values to represent the 2 triangles, if you go to something like a triangle strip, 1, 2, 3, 4, now we've got 2 triangles and we've only used 4 values, 4 vertices, because we've defined that instead of having to define each individual triangle, we define a triangle strip where the last 2 points are used to create the next triangle. So the last 2 plus a new one. In a triangle fan, we would use the first point, and the first point would always be included in the list. So these 2, so 0, 1, 2 define one triangle, then 0, 2, 3 define the next triangle. And every time we add a point to the list, it's the current point plus the previous point and the original point to make up that triangle. There are many other ways we could define primitive surfaces. This sort of represents in OpenGL that we could do triangle fans, triangle strips, triangles. We could do quads here. We could do quad strips, which is like triangle strips except for quad strips. We can do generic polygons. We can do GL line loops, when this is like actually everything in this list here doesn't define a surface. It just defines either points, or we would draw, you can imagine where we just draw the lines instead of trying to make a surface out of this, similar to the way you just have the lines here. For what we're looking at, and for glTF, WebGL standard is a trimmed down standard. And so when you get to OpenGL, that's sort of like the full sort of everything that they could possibly throw into it. And then at various points, they've kind of trimmed down the definition to only be what's actually needed to make sure that the definition for something running on the web is smaller. You'll see the same thing for some of the mobile representations of the graphic libraries. And so in the case of WebGL, definitely quad strips are not included. I think there's I think I saw they finally added quads to it, but they tend to be a trimmed down version. There's no polygons in it. So generally, while it is possible to define many ways to define a surface, for simplicity, we can really get 99% of what we want done with triangles. And so we'll focus on triangles for this, and more often than not, you'll see triangles. You'll see these others in some of the way the modeling packages create the shapes, but as part of the export process, they will often give you the option to convert all of the quads into triangles, or all of the triangle strips into triangles, just for simplicity of the platform. Again, there are always options in graphics libraries to do things that are extensible and special. So it's usually there's this balance between, are you trying to do something very specific and push the platform and use things that not many people use, or are you sitting the other end and trying to be very standard, only use things that you know will work in every view or every package. And so then when you go sort of the left end of that, this idea of the broadest standards, the least common denominators, it does make sense to just stick to triangles, and that's what we'll talk about just today. And so then when you store those triangles, the first thing you might do is you take those vertices and the list of, so we've got the list of vertices here, we've got the list of corners that make the shape itself. So in order to get those two triangles, you would actually write out in a triangle list, again in an array, the full list of all the vertices in order. Of course, immediately there's a problem with this in that you start seeing duplicates. So this vertex and this vertex are used twice, one for this triangle and one for this triangle. So it's not generally a great way because you end up to store it, because you end up storing a lot of duplicate data. So anytime that multiple triangles use the same vertex, you can imagine a full shape where there was something here and there was something here and there was something here. So this vertex might be used many times. In those cases, just listing out the vertexes that make up the triangle in order would be not a great way to store. It would be maybe slightly efficient because you don't have to do any additional lookup, so efficiency is high, but storage is also high. And so if you wanted to reduce the storage, which is something we want to do when we're transmitting files from one application to another, that's not the best way to go about it. So in order to address this, we have what they call indices. And so in this case, you have the duplicates are removed. So in this case, we've gone back to just the 4 vertices are listed here. So again, each triplet represents a vertex, and then the indices represent how do you make the triangles, the primitives that you want to see. So in this case, 0, 1, 2, and then 1, 2, 3 represent those, and they're just used individual indices representing each one. And then we had to have said that there's a primitive type, which is triangles, because if this was triangle list instead, we would have a different set of primitives. We could make this shape by going just 0, 1, 2, 3 and being done. And so it's important to know when you're storing this data, what is it actually representing? And so we need to know, obviously, that this is a vertex list, so we're expecting XYZ coordinates in order to figure out what that data represents. And then we need to know that these are triangles in order to figure out what is in the index list. And by list, generally stored in an array of data. So surface normals are something that are important when we think about normals, and I just want to take a moment to talk what a normal is. A normal is a vector that's perpendicular to the surface, and the reason why this is important is we can do our lighting calculations. We understand how bright to make each individual, in this case a quad, but a polygon. We understand how bright to make it based on the angle that normal is to the light source. And there's some nice cool tricks that make that work really efficiently. But the important thing to know is that surfaces need normals and at a base level. However, if you take just surface normals, and the surface normals can be calculated at runtime, so you could say I understand this surface as far as its shape based on its vertices. I'm going to calculate using just the cross product of 2 of the vertices would give you the perpendicular vertex, so the perpendicular unit vector. So while you can do that, the end result is if you just have a single normal for each surface, you get something like that on the left, where the shading is not it's shaded, but it's not shaded well. A better technique is to use vertex normals. So this would be calculated as part of your 3D modeling package. Each vertex would not only have a vertex point, but also an associated normal. The normal being a unit vector that represents the vector that is perpendicular to the surface. And so you get something like on the right here where we have not increased the number of vertices at all. We have the same number of polygons, but we get a much better effect because when you have these 2 points, the graphics pipeline as part of the rendering process will say, okay, well, I understand this color here, I understand this color here, and as I move across the edge, so that would be like the edge here, as I move across that edge, I'm going to linearly interpolate between those 2 points, and you get this nice gradient effect that you don't get here. Here it's a solid color. Here you would get a nice transition. So the point of this being that you get a smoother lighting if you can include vertex normals as part of your geometry definition. Yeah,
that's what I was asking.
So if we were, here again, kind of looking at storing these normals, in this case, all of the normals are perpendicular, which doesn't actually give us any additional rendering. But if we wanted to store them, this is the way we'd store them. And in this case, they all point directly up in the z direction. So these red arrows, those representing the four normals for the 4 vertices. And so we just store a list of those. Excuse me, we store a list of those the same way we store the list of vertexes. And then the end result being that for the index list, we don't need to update the index list because it's representing the exact same set of vertices. 0, 1, 2 is not just the triangle that represents the vertices of the vertex list, but also the normals in the normal list. There's a direct match between those two. So that if we were to pull out the 4th or the nth index from a normal, we would get a match with the nth in the vertex list. And that's because they're both XYZ. It's fairly easy to do that calculation. Another thing we can do is we can add color, and color maybe makes it a little easier to see how you would do that blending. So in this case, we have 3 corners. Looking just at a triangle. One corner is set to be red, one is green, one is blue, and then we linearly interpolate between them. So this would be the same way as if to the previous question. If you had a single normal at each point, you just blend between the normal positions. But you can imagine that if this was the surface of a sphere, that point, the red color at that particular point in the bottom left would be the same red color that we'd want on all the triangles that represented that sphere for that particular point, and then we'd blend across that to whatever the other colors. If you imagine if there was a purple that was in another triangle, it would go from red to purple, and then from purple up to blue if there's a triangle that was at the bottom, sort of below the one we see there. So in this case, we'd have some sort of color list, red, green, blue, and again, the index is in this case just the 3 corners, 0, 1, 2. Obviously, we don't store red, green, blue. We actually store colors in various color formats. So in this case, we've defined the color format being RGBA, where the first number is how much red, the second number is how much green, third how much blue, and the last how much alpha or how much transparency. 0 being fully transparent, so no color showing up at all, and 1 being fully opaque. And so we can use that same concept to just sort of map colors across the 3D model. In this case, you'll notice that the color list has 4 values per vertex instead of 3 values per vertex. So in order to get the first, or you've got the index list, let's say the index number 2, so the last vertex in the list, we would go to for the vertex list, we would pick the 6th or the 7th, 8, and 9 in this list if we were starting at 1. 7, 8, and 9 would represent the vertex, and then for the color list, it would be 10 or 9, 10, 11, 12. And we just use a math multiple to know that there are 4 values per vertex. And so how do we pick out whichever vertex we need in that list? We just would multiply the number of values times the per vertex times the index the index item. So if it was 0, 1, or 2, and then we would end up with the right set of values and corresponding to the right set of values in the vertex list. Next slide. And we're at 12. Do you want to?
I don't have. Yeah, I mean, I'm good to continue, but if you have to go, then we can pause and pick it up later.
I think I can go. Let me double check. I'm pretty sure I'm free here. Yeah, I can go for a little bit. We'll see if it ends up going too long, then we'll pause it. But go for another 15 minutes. We're getting through the hard part. Okay, so then more often than not, the way that we actually render information is especially color information, is actually through textures. So while you can go through and color each individual vertex, that's not a very efficient way to work from an artist perspective. And so what they'll use instead is they'll use textures, and then the textures are mapped with what we call UV coordinates. So that's just the X and Y sort of percentage across of the texture that each vertex represents. So in this case, I've got a texture in that top left with a smile, and you imagine the bottom left corner of that is 0, 0, and the top right corner is 1, 1, and then we use some percentage value from 0 to 1 as UVs to map onto the surface of the image on the right. So in this case, we've just mapped a quarter of it by saying that the top right vertex aligns to 0.5, 0.5 in the texture. And so we can just define the 4 corners and what those 4 corners represent as far as where on the texture they should be drawing their data from, how they map to that texture, and then the graphics pipeline just does it magically for us. And so I've highlighted in red one set of one corner. So that would be that top left corner. You have the vertex 1, 0, 0. You have the UV coordinate 0, 0.5. And then you have the index as 1, and that's how they show up in that list down at the bottom there. You also need to define what texture it is. So in this case, it might be smile.png. You can have multiple textures, and you can have multiple. If you have multiple textures, you'll obviously have multiple UV lists. So this is going to be super important when we move from a solidly rendered shape in something that's more sort of proof of concept to something that someone actually used. They would actually use textures on the shapes. So just as a base, some of the information that we've covered and sort of the base of what you would need to get a shape. We've got sort of vertex list, normal list, color list. Once we have the color list, we have to have the color type, so we know how to go across that data set. We know that now that's 16 values total in this list of 4 sets of 4 colors. The normals are 4 sets of 3. The vertexes are 4 sets of 3. We get down to the UVs. That's 4 sets of 2. So 8 values, and then we get to that index list. That index list represents 2 triangles, so 6 values or 2 sets of 3. So when you're doing all this, although you have these long data arrays, it becomes really important to know what the data actually represents, because it could be triangles, it could be triangle strips, and for color types, it could be RGB, it could be RGBA, it could be ARGB. There are multiple ways people might do it. These are probably the more common that you'll see as triangles and RGBA, but it's important to keep track of these so you know what you're actually what the data represents. So then jumping into the actual transmission format, which is glTF 2.0, which is kind of what our focus is. We're really representing both JSON and binary data. So one of the things to understand, of course, first is that there are lots of different types of polygonal file formats. Some are proprietary, like FBX. Some are very simple, but very completely text and readable, like OBJ. And OBJ, if you open up that file type, you can very easily see what in written in text what the values are, and you could even open it up in Notepad and start editing right in the text file, and have that update in a way that is to be expected. glTF, when I first was talking about glTF, I thought glTF was OpenGL's text format, and it's definitely not a text format. The T does not stand for text, it stands for transmission, and these files themselves are built of a text component for readability and for hierarchy, but not with the expectation that you would actually edit that text in a text reader because of the way the data is stored. And then there is also a binary component to that, and we'll go in a little bit more about the binary component here in a minute. Note that most CAD files are not polygonal. Again, they're using they want a much higher level of precision, especially when you zoom in and zoom out of the data set, and so they're using mathematical formula to represent the various shapes, the curves. You can imagine if you had something like our sphere that we saw at the beginning, and you had it represented by these polygons with a very jagged edge. It might look really well rendered, but if you actually try to cut that out as a shape for use as a piece of machinery, if you use polygons, eventually you're going to have a very jagged edge because you just have surfaces that are represented by connections between points, and you want a lot more detail, and that's only going to be able to be generated by using something that is vector-based as opposed to polygon-based. And one of the challenges that we run into, obviously, is that a lot of the expectation for people using our apps is that they've got CAD files and they want them to show up in our tools, and it's not nearly as simple as just saying, well, make it work. When you move from a CAD file to a polygon file, you're going to have a loss of data, and that loss of data is one way because you're losing a lot of information, and it is what data you lose and what data you pay attention to is going to be very dependent upon the industry. And so what we may, if we had built a solution to kind of transcode CAD files into glTFs, we may be picking the wrong data to pay attention to as data is lost. And so we definitely, at least at this point, are on the side of an individual knows or should work with a third party to figure out what's the best for their industry, because there is no generic solution for CAD to glTF. So diving a little bit more into the glTF itself, and I guess going back a little bit, again, this data on the left is worth noting. That's the data we're trying to store. So going into sort of the glTF standard, this graphic is taken from the standards page, but there is this top area, which is the scene definition, so nodes, meshes, cameras. It also includes visual properties that you're going to use, so materials, as well as any references to where the binary data is stored, and how to understand that binary data, because the binary data, again, is just going to be an array of values. Then we've got the .bin file, so the binary data itself. That is going to include all of the geometry that we just covered, as well as animation and skins. We kind of skipped past that. The important thing to know with animation and skins is it's just more data. It's stored in a particular way, and it can be dug into, but there's very little that actually would change anything to do with the data format, other than to know that there's more data there. And then in addition, there's this idea that there's a representation of textures. glTF supports both PNGs and JPEGs. The two obviously being, one is a lossy format and one is a lossless format. So looking directly at this idea of glTF in multiple files, in the data on the left that we're storing, sort of the overall sort of metadata about the file is stored in that glTF file. And so I've got an arrow on the left there that points to the data that we were storing before, and then on the right, how it starts showing up in that JSON and what it might look like. And then on the binary file, which is the next one down, is where we actually store all of that additional binary data. So the actual values get stored in that .binary file. And then we would additionally have PNGs for the textures. So it's worth noting that on the right there, the kind of things that you're going to see as values in the JSON is buffers, buffer views, accessors, and we'll talk about those. There are scenes, nodes, and meshes, and then cameras and materials. And so that's all of the data that's stored in that as that metadata, which is in the JSON. And again, the binary data is going to be that data on the bottom left. So if we're going to store this data, we got to store it in a single buffer. So that's a single binary file, and we're going to have to pack it all in there. And so the first thing we're going to do is kind of split the data into groups representing by the type of data that's stored in there, the components that's made of. So for vertices and normals, these are groups of 3 values. So in the case of 4 vertices, we have 12 values, 3 floats represent an XYZ coordinate, and then knowing that each one of those floats is 32 bits, we can do some calculation that each value is going to be three 32-bit chunks, and then in this case there's a total of 12. For the color list, there's 4 floats. For the UVs, there's going to be 2 floats per vertex, and then for the index list, it's no longer we're talking about 2 per vertex, but we're talking about how many vertices make up a triangle. And so for each indice, it's going to be a single bit representing that vertex. And then we know that there's 6 values because there are 2 triangles with 3 vertices per triangle. So this is just as we start thinking about how we store this. And so we're going to store this in a single buffer, but it's going to be the buffer view that glTF uses in order to divide up the buffer itself. So in this case, I've got 4 different buffer views, 1 for each one of those categories of data. So when the byte stride was 12, in other words, 3, is that right? 12 is that? I might have got my math wrong there. I think there should be byte stride is 9. Anyway, ignore that. But the idea being that there's a common stride for no, that's right. For 32 is 4 bytes. 32 bits is 4 bytes. 4 bytes times 3 values is 12 bits, or 12 bytes. 12 bytes. And so that's how each vertex is represented by 12 bytes, 3 values with 32-bit float per value. And so if we had 10 vertices, it would be 10 times 3 times 32 or 120 bytes. And so that's the vertices and the normals. The colors, they're going to be larger because they've got 4 bytes per value. Sorry, 4 values per unit of data, and that's 4 bytes for each one. So 16 bytes is required to have 1 color for 1 vertex. And again, this is how we're separating the buffer views as opposed to the buffer itself. So a single buffer, but many views to represent the type of data that is stored in each one. Specifically, the data being different by the stride that each unit of data takes up. So in this case, vertices and normals can be combined, whereas we couldn't combine vertices, normals, and colors because they have different byte strides. The buffer view is defined by an offset and a length, and so in this case, it becomes that buffer view 1 has a byte offset, which is equivalent to the byte length of the first buffer view. So you can calculate as you go what the offset is. You can calculate the length based on the stride and the number of values, and then so you can sort of do the math as you work your way across the buffer. So now zooming into a single buffer view, your buffer view might have multiple accessors. And so an accessor is the way we're going to say, hey, this mesh is made up of these vertices. These vertices are going to be stored in a particular accessor within the buffer view. So we have, in this case, we have 4 accessors. The first one is the vertices for mesh 0. The second one is the normals for mesh 0. The third one would be an example of a mesh that didn't have any normals defined, and then another one with no normals defined. So this sort of represents the way you would walk across a buffer view, again with offsets and lengths, to figure out how do you figure out where are the vertices within a particular buffer view.
So the first mesh has vertices and normals, and then the next 2 don't have normals defined.
Correct.
Okay.
Correct. And just I did that to show that you don't have to have everything defined in each one. You could easily have a model that didn't use vertex normals. In addition, you could have other data as we look at some of the other accessors. So just being very much aware that it's going to be the JSON that determines how do we read this. And so that'll be, when we look at the JSON, we'll see how it knows what to pull out from any particular accessor. So again, just sort of covering it again, there's kind of binary metadata that's in the JSON, and then there's the scene hierarchy information that's in the JSON. So the binary metadata is mainly pointing to, once we know that we have a buffer, where do we find things in that buffer? And then the scene hierarchy is going to have a little bit more information about how do we build a 3D scene based on the data that we've pulled out from the binary file. So looking here at the JSON, and that last one looks like it's a little blurry, but so be it. In this case, we have a buffer defined in the JSON, which says, okay, there's a buffer. It's an array of values. In this case, there's only one value, and it has a byte length of 648 and a URI of box0.bin. So it's referencing an external file. And in the second image that's turning out blurry, it's showing that that is an actual file in the file system, and that there is that it has a size of 648 bytes, which is corresponds to what was referenced in the JSON. Alternatively, you could have your binary data stored in a base 64 encoded string and embedded directly into the JSON. So in the second case there, in the bottom case, you don't have a second file, you have a single glTF file, and all of your binary data has been converted to a text string, base 64 encoded, and just laid out as a long text string within that JSON file. Obviously, again, this sort of goes back to this idea that this is not exactly a thing you would go in and edit by hand. You can open it in something like Notepad and read it, but whether or not the information in there is something that you would modify and then have a good result from is definitely it's not the case. So then once you have the buffer defined as something like we have in the top, then you have the buffer view, and the buffer view in this case says, okay, for this buffer view, what buffer do we look at? And in this case, it's buffer 0, because there's only one buffer. It's the first 0. And the second set of data there at the bottom where it says buffer 0, byte offset 0, that would be the start of that buffer. And it has a length of 576, and that has a byte stride of 12. And so we know that there is a set of data in there where each value is 12 long and 12 bytes long, and for a byte length of 576. And then so we go to the previous definition there, which is actually the second buffer view, the first buffer view in the definition, but the second set of data. So we don't have to have the buffer numbered in a particular way. The buffer view is numbered from left to right. It could be however we want to define it. In this case, the 0 buffer view has an offset of 576, which is the continuation that we got from byte length below it, with a byte length of 72. And that target value is whether or not it's either an array buffer or an element array buffer, and that's just an internal value that's stored. And then when we get to the accessor side, the accessor then points to the individual setup within each one of those buffer views. So in this one, the first accessor that's defined points to buffer view 0, and the second one points to buffer view 1. So the two sets of data that are defined in the buffer views. Then that's when we then get into the more detailed data, which to say, okay, here's the offset within that buffer view. So it starts at the beginning of the buffer view. The type is 5123, which I've called out there, which 5123 represents unsigned shorts. So this is the indices are in this case stored as unsigned shorts. There it shows you the count. So there's 36 indices. So we could do the math to say that an unsigned short is 4 bytes. And so if there's 4 bytes and there's 36 of them, that's how we get to, 2 bytes per unsigned short. So a short is 2 bytes. So 2 bytes times the 36 gives us the byte length of 72 that we see there in the buffer view. The definition for glTF also wants to know the min and max values that are inside there, which is means that the smallest index is a value 0, and the highest value of index is 23. So you can see that although there's 36 times that indexes show up in this set, the highest number of index is 23. So there's 23. What we see from this is actually there's 24 vertices that make up the various triangles in here. Similarly, the next set of data there, the buffer view 1 points to the accessor 1 points to buffer view 1, which again points to buffer 0, and a certain byte offset, which in this case is 0. So it's the start of that byte, that buffer view. In this case, the component type is 5126, which is floats. There are 24 floats, and they're grouped in 3s. And we know that because the type is vector 3, which is at the bottom there, and then we have minimum and max values, so of -1, -1, -1, and 1, 1, 1. So that's when we know that this particular group of data is going from a max value of 1, 1, 1 and a minimum value of -1, -1, -1. So that's basically the way you would look at a bunch of data within a JSON glTF file and make sense of it. And because these values point to other arrays within the system, you could imagine just the same. It is not something the expectation is that you'd go and manually change any of this data. This data was built as metadata from what is stored in the binary data. So going to sort of the next level, which is the scenes, nodes, meshes, and materials area. In the middle center there, I have a material definition, which we won't go into too much detail in this presentation, but just basically talk that's the way you define a material or the way you render the object. And then the scene hierarchy is made up of a scene, which is there's a single scene. In that single, for this example, there's a single node within that single scene. So that's what's defined at the left. Which node? Well, node 0. There's only one node defined, and that's in that second box. So the node has a matrix, which is it looks like a very simple matrix, but that's the representation of 16 digits as to how the translation and scale and rotation is represented. That's a whole different topic of how you store the scale, rotation, and position in 16 digits, but it's stored as a 4x4 matrix. And then we reference mesh 0. So then you go into the mesh section to figure out what the mesh is all about. And in this case, the mesh is primitives. And what kind of primitives? Well, it points to a mode of 4. And so mode of 4, going down to look at the values, 4 is triangles. So this is where we see that points, lines, loops, strips, or triangles. And so that's saying we get a bunch of triangles. Well, where are the triangles? The triangles are defined by indices, which is an accessor 0. So accessor 0, we looked at earlier, which points to a particular buffer view, which is a particular buffer. The normals, the attributes, there's normals and positions. So the normals are stored in accessor 1, and the positions are stored in accessor 2. We've already looked at both of those. And then we've got the full definition of what the primitives are. In this case, what we're looking at is a cube, and this is we'll look at the actual I think it's called box within the sample glTF files that are out there. But this is how a box is defined. So again, sort of noting the simplification, we've ignored skinning and animation. Both of those concepts are around how do you animate this stuff. We've also skipped through the details of materials and cameras, as well as the difference between samplers and textures. But we've covered the majority of the concepts, and the most important, I think, for getting started. You can't really understand any of the other stuff until you understand these basic concepts. But there are some limitations in what we just described. In the limitations of a basic glTF, multiple files are not great. So if I say, hey, I want this glTF file, and it comes back and says, okay, well, we're going to give you this glTF file, but you also have to grab the associated images and binary data. That's not great. The alternative we looked at is where you do the base 64 encoding. By doing the encoding, converting all the data so it fits into string value, generally adds about 33% to the file size. And it also adds a step of requiring a decoding step of converting that base 64 encoded string back to binary data. So there are both limitations on either having a bunch of files that you have to go and fetch separately, or having all of that binary data stored in a big string. You're adding both time and size to your glTF. And so then the question becomes, well, how do we improve that? And so the improvement is in the GLB files. So GLBs are binary glTFs, and they're pretty simplistic in their design. The first three sections on the left there. So there's a 12-byte header. Excuse me, 12-byte header. The first, and we'll actually go into each one of these in a separate slide. But the first section is header data. The second section is going to be the JSON data, so similar to the text file that we saw before. And then the third header is going to be the binary buffer, all stored as part of that single file. We have the option of, instead of having a GLB where all of the data is stored in the GLB file, we could also have a GLB plus a binary file, which is what that external data points to. But that kind of defeats the purpose of a single file. But I think it does allow you to say, well, the definition of a binary file for a GLB is the same format that you would use if you were using a glTF. So you could easily convert a glTF's binary to actually be encoded as part of a GLB's binary. So looking at the header, there's 4 or 3 values. Each one is 4 bytes. So the first one is just sort of this magic number, and it just resolves to the ASCII representation of the letters glTF. The second is the version. In this case, it's version 2.0, or just they write 2. So basically, the first 8 bytes are going to be, for almost every GLB out there, the exact same. And then the length is the total length of the entire file. And so when we do a validation step, there'll be a check to see if the length defined in the header actually represents the same number of bytes that are stored in that the entire file is made up of, the entire GLB. So then looking at this a file, I've got this GLB file that I'm looking at Notepad. You can see that that magic number shows up as just literally glTF. 2 doesn't show up in ASCII because it's just the number 2, and that is not an ASCII value that's going to be readable in Notepad. And then when we get to the length, that's that with a funny character after it. That's just whatever a notepad is using to render the data that's stored where the length is stored for this particular file. But then immediately goes into a set of JSON, which we'll see in a moment here. So for the chunk the 0, which is the one we just looked at, we have a fairly straightforward definition of what the data includes. For the but as part of that data, or as part of the second set of data, what we need to know is when we're looking at the second set of data, which is chunk 1, we have a length, which is the length of the chunk data. So it's not a length of the whole file or of the header, but what is the length of the chunk data? So the binary buffer. And then what is the chunk type? So for chunk 1, the expectation is this is our, I think I skipped over a part. Let me go, yeah, I skipped over something. Oh no, it's because they gave it, yeah, I always get confused because this middle section is called chunk 0, but it's actually the second set, so I skipped over something. So let me go back to this. So we've got chunk 0. So chunk 0 is the second set of 3 data in the previous slide. But this is the first bit's the chunk length. So how long is the chunk data? The second set is the chunk type, which in this case it's going to be a magic number, which results in the word or the letters JSON or JSON. And then the third section is our actual data, which is the JSON file. And it's the exact same JSON file we had in the glTF, but just converted to be what is the actual binary representation. So taking that ASCII, those ASCII values, and instead of representing them as simple ASCII values, representing them as their 4-byte equivalent. So that just ends up being chunk 0, ends up being just your JSON. And then inside of that JSON, if in the buffer definition, if you said there is a URI that points to a particular binary file, then it's going to use it as the old one did. But more interestingly, if you do not define a URI, the assumption is going to be that this third chunk 1, or the third set of data, chunk 1, is going to be a binary buffer. And that's going to, again, length and type. In this case, the type is going to be the magic code there, which comes up to bin, and then the total file and lengths. Total file length is going to be that says I got to update that. That shouldn't be total file length of bytes. The chunk length is the length of the chunk data only, and the chunk data is actually the data that is our binary data. So ignore that misquote there.
So what happens to like the other stuff, like the images and stuff like that? Are they
That
just
should
extra
also
images?
that's a great question. That should also be included in the binary buffer array, and I don't have a good example. I haven't gone through as to demonstrate how that's done, and I need to do that for myself. So that's addition I want to make to this slide, is showing how you take like a PNG data and also shove it into the binary buffer in addition to all the other data you have in there.
Okay.
For this, we're kind of simplifying and saying we're not dealing with textures, but for this particular presentation. But yes, that's how it would be done. So I'm looking at this in something like that includes like a hexadecimal view. You can see for this data how this starts showing up. So we've got the magic number resolving on the right to glTF. The version is, and I'm looking at real data, so it says version 2 right there as the 4th column in the first line, and then the hexadecimal representation for the length, and that's what shows up in that sort of that first the header part of it. So then we get to the JSON chunk. You can see that JSON is at the start there. The chunk length is represented in column CD as 5404, and so that corresponds to obviously what the length actually is. And then you notice that in the type is going to be that magic number, and then it shows up as JSON, and then the rest of the data is actually just text data.
Okay.
And then for that last bit, we got a bunch of binary data. Again, just representing it in an ASCII file doesn't really mean anything, but you can see that the letter BIN shows up in the chunk type, and then you've got the length is encoded there as well, and that obviously is a little longer than the other one because it's a bunch of binary data. So, quick review: 3D models, they're a combination of vertexes, normals, UVs, textures, materials, cameras, bones, skins. glTF is not a text format, but it includes a slightly readable, not necessarily editable because all of the data is interconnected, but includes both the scene, node, camera, matrix, materials, and all of the metadata for the binary file, and then also the binary data stored as vertices, normals, indices, as we mentioned. There are 3 primary ways that this data can be stored. On the left, we have that first way, which is that there's a buffer and a binary file. And so if you look down at the bottom left there, it shows how that would show up in a repo with the glTF and associated binary file. In the middle one, we have one that is a embedded glTF where the URI is actually included in the string there. And so we only have a single glTF file. And then the last one, we have a single GLB file, and then the URI is not defined, but is as part of the end of that GLB file. There is a 4th type, which is uses Draco compression. Just ignoring that has an extra step of needing to compress the file, but that's generally used for the first 2, and it's not as needed as much in the last one because we don't have that same increase in size. Although I believe it can be. I need to do a little bit more research on Draco itself. So theoretically, at this point, we've covered the course concepts. We've covered the storage options. We've covered the JSON and how to read the JSON and understand what's inside of it, and we understand how the binary data is packed. Any questions?
Great. As of now, no, I think you were pretty clear. I think I'm going to review by watching the recording. But yeah, no questions right now.
Cool. I've got links in the deck, and I'll get the deck to you a little bit later. But it's to the spec itself, which I think you've already found. Sample models in GitHub, and then a little bit of data on Draco compression for interest.
Cool.
Cool. Okay. Well, I'm gonna go get some lunch.
Awesome. Thank you so much.
Yeah. Take it easy. Bye.
You too. Bye.